Welcome to the lesson on continuity and differentiability. Intuitively, we say that a function is continuous on an interval if its graph can be drawn without removing a pen from a paper. For example, the graph that you see here is an example of a graph that is continuous everywhere. We say continuous everywhere if it is continuous at all values of x in the set of all real numbers. As you could see, you can trace the graph of the function without removing a pen from the paper. It will just continue to go on up to infinity. On the other hand, when a graph is broken or disconnected at a particular value of x, let's say for instance in the example here, the graph is disconnected at x equals 2. This function here is said to be discontinuous at x equals 2. Now if you also examine, if you plug in 2 to the function is not defined at x equals 2. But if you look at the limit of the function as x approaches 2, if you trace the graph as x approaches 2 from the left, the graph will approach this point here, which is y equals 4. And also, if you look at the graph, or where the graph would approach to as x approaches 2 from the right, the graph will also approach at the same point, which is y equals 4. Therefore, we say in this case that the limit of the function as x approaches 2 is equal to 4. But again, the graph is not defined at x equals 2. In this example, we see a case wherein the limit of the function exists at a point, but the function is not defined at that point. And in that case, the graph is discontinuous at that value of x. In other words, if the function is not defined at a particular value of x, automatically the function is discontinuous at that x. Another example. This graph here is a graph of a function that is discontinuous at x equals 0. As you can see in the graph here, the graph has a jump at x equals to 0. And also, the limit of the function as x approaches 0 does not exist, because if you evaluate the limit of the function as x approaches 0 from the left, you get -1. And the limit from the right is +1. So therefore, the limit here does not exist. And moreover, if you look at the graph at x equals 0, you see a hole on the graph, so that this means that the function is not defined at x equals 0. Now, based on the examples here, we see that for a function to be continuous at a point, the function has to be defined at that point, the limit exists at that point, and the limit and the value of the function at that point are equal. Now we see from this example that if one of those three conditions are not satisfied, then the function is discontinuous at that point. Say for instance at x equals 2, this function here is discontinuous because the function is not defined at x equals 2. And also, if the limit does not exist at that point, then the function is discontinuous at that point. Hence, we have the conditions here to be satisfied for the function to be continuous at the point x equals c. First, the limit has to exist at x equals c, or the limit of the function as x approaches c exists. The function is defined at x equals c, and the limit and the value of the function at that point has to be equal. And moreover, we say that the function is continuous on the open interval ab if it is continuous at each point on the interval. Now, in the example here, we are given the graph of the function f of x. We will use the definition of continuity to discuss the continuity of the function. So based on our discussion, if there are gaps or holes on the graph, that means that the function is discontinuous at that point. So the function is discontinuous here, 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 and in here. Then let's just go ahead and identify the value of x corresponding to this point. This is the point 1, 2, 3, 4, negative 4. So it is discontinuous at x equals negative 4. At x equals, this is negative 2. And at x equals 1. And also at x equals 4. Now, using the definition of continuity, let's identify which condition was not satisfied at each value of x. So at x equals negative 4, the condition that was not satisfied there is that the limit of the function does not exist at x equals negative 4. So if you look at the limit of the function as x approaches negative 4 from the left, so coming from the left side of negative 4, your function values approaches to this point here, which is equal to 2. While if you take the limit of the function as x approaches negative 4 from the right, so coming from the right side of negative 4, your function values approaches to this value here, which is equal to 3. Now, since the left-hand limit is not equal to the right-hand limit, then we say that the limit of the function as x approaches negative 4 does not exist. That same explanation too holds for x equal to 1. At x equals 1, we could say that the limit of the function does not exist because its left-hand limit is not the same as the right-hand limit. And at x equals negative 2, your function there does not exist. So therefore, the second condition is not satisfied in this case. And lastly, for the case when x is equal to 4, in here we see that the limit of the function exists. So if you get the limit of the function as x approaches 4, it exists because coming from the left side of 4, the function values approaches to this point here, which is 3. And also from the right side of 4, the function values is approaching to the same point, y equals 3. So we say that the limit exists. But if you look at the value of the function at x equals 4, f of 4 is equal to this point here, which is equal to 1. So these two are not equal. So since these two are not equal, then we say that the function is discontinuous at x equals 4. Another example. Use the definition of continuity to discuss the continuity of the function f of x equal to x plus 3 at x equals 4. To do this, we would need to satisfy all three conditions. So first, let us examine the limit of the function as x approaches 4. The function is defined as x plus 3. The limit of x plus 3 as x approaches 4 is equal to 4 plus 3, which is 7. So the limit exists. Next, let's look at the second condition. Is the function defined at 4 at x equals 4? Let's plug in 4 to x here. We have 4 plus 3, which is also equal to 7. Now, third condition is that these two here must be equal. Now, we have seen that the limit of the function here, x plus 3, as x approaches 4, is equal to f of 4. So all three conditions are satisfied. Then, therefore, we say that the function is continuous at x equals 4. Next, let's use the definition of continuity to discuss the continuity of the function g of x equal to x squared minus 9 over x plus 3 at x equals negative 3. Now, by inspection, if you plug in x equals negative 3 to the denominator of g of x, we say that the denominator is 0 at x equals negative 3. So in that case, we can then conclude that g at negative 3 does not exist. Now, if you want to prove discontinuity, you just have to find one condition that is not satisfied in the definition, and that is already sufficient to say that the function is discontinuous at that point. So from here, we can say that the function g of x is discontinuous at x equals negative 3. But then if you want to go ahead and look at the other condition, which is the limit of the function as x approaches negative 3, you can go ahead and compute for the limit of x squared minus 9 over x plus 3 as x approaches negative 3. You can obtain the limit by simplifying the function by factoring. You can factor the numerator as x minus 3 times x plus 3 divided by x plus 3. This factor here will cancel out. And then you can plug in negative 3 to the function here. You get negative 3 minus 3, which is equal to negative 6. So this example is the case wherein the limit exists, but the function is not defined at that value of x. Therefore, the function is discontinuous at this x. Another example. Let's discuss continuity of this function at x equals 1. First, let us look at the first condition. Let's find the limit of the function x, absolute value of x minus 1 over x minus 1 as x approaches 1. Now, if you plug in 1 to the x here, you get 0. And then if you do the same thing in the denominator, you also get a 0. And so we get an indeterminate form. And to evaluate this limit, since we have an absolute value here, we would need to split our limit into two sides. We would need to evaluate the limit of this function as x approaches 1 from the left, and also find the right-hand limit as x approaches 1 from the right. And then to evaluate the limit here, since we would still get 0 over 0 when we plug in 1, we will just have to get a representative point at this interval. So you get a value that is less than 1 but is very close to 1. Say for instance we get 0.99. So we get 0.99 minus 1. And then you do the same thing in your denominator. So your numerator would always be a positive number, constant, which is greater than 0. But your denominator will be 0. And if you have 0.99, so let's look at the sign. So 0.99 minus 1, you have a number that is less than 1 minus 1. That gives you a number that is negative. So you have a 0 minus there. So if you have constant, which is a positive constant, divided by 0 minus, that gives you negative infinity. Remember, constant over 0 is infinity, and then it follows the rule of signs. Similarly, for the right-hand side limit, you get a representative point at the right side of 1. For instance, you get 1.1. 1.1 minus 1. Absolute value of that is still a constant, a number that is greater than 0. And the denominator, you have 1.1 minus 1, which will be 0, but positive, because 1.1 minus 1 is positive. So you have positive over positive, that is positive. And constant over 0 is infinity. So you get a positive infinity. Here, from here, we say that the limit of the function h of x as x approaches 1 does not exist. And since the limit does not exist as x approaches 1, then we say that h of x is discontinuous at x equals 1. Another example. In the example here, we are given a piecewise function and we want to discuss the continuity at each of these points. So we want to know if the function is continuous at each of these points here. Now we start at x equals 0. Now notice that x equals 0 is an endpoint of the interval here. So therefore we suspect that the function may be discontinuous at this point. So we do that by first examining whether the limit at x approaches 0 exists. And since this is a split function or a piecewise function, let's go ahead and find the right-hand limit and the left-hand limit of the function. Now, at the right side of 0, your function is defined as 4 minus x. So x approaches 0 from the right means right side of 0 or greater than 0. When x is greater than 0, the function is equal to 4 minus x. And then evaluating the limit here, we just plug in 0. So we have 4 minus 0, which is equal to 4. And then next, if you take the limit of the function as x approaches 0 from the left, 0 from the left means at the left of 0, left 0 is less than 0. It means less than 0. So when x is less than 0, the function is defined as 2x plus 6. Now when you plug in 0 to x here, you get 6. Now you see both of these limits exist, but they're not equal. So since they are not equal, these two limits here are not equal, then we say that the limit of the function does not exist. So therefore, the limit of h of x as x approaches 0 does not exist. Now, since we have seen one condition that was not satisfied already, the limit does not exist, therefore, we say that the function is discontinuous at x equals 0. Now, let's discuss continuity at x equals 4. So first, let's find the limit of the function as it approaches 4. Now, 4 is on this interval here, and 4 is not an endpoint of the intervals here, or the endpoints of the inequalities here. So therefore, we do not need to split our limit into two sides. We'll just go ahead and find the definition of the function at x equals 4. X equals 4 is on this interval here, and therefore h is defined as 4 minus x. Now the limit as x approaches 4 of h of x will just be 4 minus 4. And 4 minus 4 is 0. So the limit exists and it is equal to 0. Next is to find the value of the function at x equals 4. So let's find h of 4. Again, h of 4 or 4 is on this interval here, and we use this definition of h for x equals 4. So we have 4 minus 4, which is 0. Now, we've seen that the limit and the value of the function at that point are equal. Then we say that the function, so we say that the limit here of h of x as x approaches 4 is equal to the value of h at 4. And so therefore, all three conditions are satisfied. So therefore, h is continuous at x equals 4.